In this video of StressOff, we are going to use Salome-Meca as the software of choice to conduct finite element analysis. When you open Salome-Meca, this is the window you get. First, we'll go and select Geometry module, in which we can go in Primitives and select Box, or we can just select Box from the list here. The dimensions that we want for the box are 1000 by 1000 by 1000 in length, width and height. Now, as far as the geometry is concerned, the geometry has been created. The only thing that we need to do, and this will be useful for conducting finite element analysis, not just in Salome-Meca, but also in other softwares, which we'll look into other videos for, say, for example, Calculix. We'll create some groups. Now, the main group that we want to create is press or pressure on the top face. Next, we are going to create bottom face as DZ0. Now, the bottom face, as we always do 3 types of boundary conditions. For the first case, we'll just do DZ0 for the bottom case. In next scenario, we'll use DZ0, but also add DX as 0. For that, we'll have to go in and select the shape type of edges only. When I select this edge, we will need to create this as DY0 because we are going to constrain this edge in Y direction. And next, we are going to constrain this edge in X direction. So we'll just say DX0. Now, after we have created all of those different groups, we are done in conducting or creating the geometry in Salome. Next, let's go in and mesh this geometry. So we go in mesh and then we select this button which says create a mesh. We'll just say we can give it any name. We'll just keep the default name of mesh 1. And then for the algorithms, we'll just select NetGen 1, 2 and 3D. In NetGen 3D parameters, just to keep everything consistent, we are going to go and say max size we want is 100 and we'll keep everything else the same. Now, there are other things like we can do chord dominated mesh, or we can also do second order mesh. We're just going to leave everything default here. I'll say apply and close, and then we will go in and compute this mesh. Now, as you can see, mesh has been generated. So we can close this safely and we can see what type of mesh has been generated. Now, let's just, for the sake of making sure that the meshes are same, let's just count how many divisions were made on this one single edge. 1, 2, 3, 4, 5, 6, 7, 8, 9 and 10. So this 1000 millimeter edge was divided into 10 segments, as what we have done with all the other softwares, the videos that we saw previously. Next, let's go in and create group from geometry. Now we'll create all of these 4 geometry groups that we created in the geometry module. We'll add that for the mesh group. We'll also say not just the element group, we'll add them as node group as well. I'll click on apply and close. So thus we can see that we have all of these groups of nodes, edges and faces. Now we are deviating a bit here and I'm just showing you how to export this mesh for use with other softwares like Calculix, which again we are going to use the same file in Calculix. So to do that, we just do export UNV file, and in Calculix we'll pick this file up and we'll conduct finite element analysis that way. But before we do anything, let's just first save this file till now. We'll create a new folder and we'll call it Salome-Meca, and we'll just say this is case 1. Okay, in this, let's go in and export this mesh to UNV file. So we'll call this again mesh_1, and we'll just save this, and we'll pick that up in Calculix. Now there are a couple of ways in which the next section can be done. So there are ways in which we can go in and create the study file in StressStudy. This is the default module that comes with Salome-Meca, and we can definitely go in and have a look here, but there is an easier alternative. This software is called Efficient. So just let's quickly go through the tabs of how to conduct or generate a command file. So mesh type, we are just going to say it's a med file, and the type of calculation is linear static. Analysis type is mechanical 3D. Material is carbon steel. Young's modulus is 2.1 E5. Again, we are using millimeters, megapascals, we are using tons, all of those units. That's why density is tons per millimeter cube. Now it is assigned to all. We'll just click that and add this in. Now we don't need to add any element type because there is no beam or there is no shell element in here. For the boundary condition, there are a couple of things that we need to do. So for the first one, degree of freedom, let's just say dz0, and it's assigned to dz0, and we'll just say dz0 is 0. So this is the very first boundary condition that we are going to add. For next, let's go in and add a load of pressure, and we'll just say it is applied on press, which is the group name or the phase name that we created, and the amount of pressure is 1 megapascal. And for the output, we can go in and say we want all, or we can say I just want the 1 µ stresses on the nodes. So let's just go in and add that and just make it simple, and we'll just call it case 01 dash dz0. We'll save this file. Next, we are going to save another file in which we are going to make sure that dy0 is also used, and we'll make y as 0, and then we'll just say dz0 dx0, not dz, dx0, and we'll just make x as 0 as well. Everything else remains the same. So we'll go in and save this command file, and we'll just call it dx dy dz0, and we'll save this command file as well. Next, we are going to just delete all 3 of them, and we are going to add a boundary condition which is called fix, but we'll assign it to dz0, and we'll just add 0 to all. We'll add 0 for all 3 degrees of freedom, and then we'll call this command file as fixed. Save it, and then we can exit from here. So again, back to Salome-Meca, and we can just go to current case. We can say add stage from file. In here, we are going to use this command file that we just created, in which dz0 phase, or the bottom phase, will give the boundary condition as dz0. So that generally happens because mesh file has not been selected yet. So we'll just say okay, and we'll go all the way down, and in here, this file, we'll just call it case 1 dz0.rmed, because that is the result of the med file, and I'll just say save. When that is saved, just click on OK, and then we'll go to history view, in the current case, we'll keep everything same. The memory allocated is nearly 2 gigabytes, and I think that should be enough for this simple case. So I'll just say run this case. Let's just refresh this, and we have an error. So what's the error? Let's just copy this in Google Translate and see what result we get out of that. Let's copy it here. Okay, it just, out of all of that, what generally it means is that there is no way that you will be able to hold this analysis. So in other words, if you just provide DZ0, it was all right for PrepoMax, it was all right for FreeCAD, and it was also all right for ANSYS, but for Salome-Meca this won't work. So how about let's just keep this case as it is. We'll have to go in and change this case from DZ0 to, we'll just make use of the dx dy dz equals to 0 file. Again, we'll have to do the same thing. Let's add the mesh, and let's go all the way down and save this file as an RMAD file. Let's say okay, save this, and then let's go back and run this analysis. We have got auto refresh at 5 seconds, and again, as you see, the case was all right in running. So we have an output which can be seen here. To get the results or to do the post-processing, we can just do simply right click and then post-process. And this is the result that you can see. Now here, this is the displacement, and again, this displacement is for all the 3 directions, X, Y, and Z. Now the displacement that you can see is 0.0052 millimeters or 5.2 micrometers. That's the magnitude of it. How about let's just go in and say we'd like to see DZ displacement only. Here you can see that DZ displacement, for the DZ displacement, the minimum displacement you can see is minus 4.8 micrometers. We'll again compare all of these displacements in a final video where we'll collate all the displacements from all of the softwares that we have used, and then we can compare whether the displacements and the finite element analysis results in one MySys are matching or how close they are with each other. So the displacement DZ is 4.8 or negative 4.8 micrometers. Displacement magnitude was 5.2 micrometers. And let's have a look at the equivalent stress in one MySys. As can be seen, the entire cube has a stress of 1, because as you can see, nothing has changed. So the entire cube has a stress of 1 megapascal. Now this is one of the boundary conditions that we used. Next, how about we just go back to case view. Let's delete this command file, and then we'll just add another file which has the fixed boundary condition for the bottom face. So again, let's go in and say mesh_1 is the mesh file, and for this it is for saving, we'll be saving it as case01 fixed.rmad, and we'll say okay. After that, let's go back to the current case, add that one in, and let's just run this analysis as well. Again, this analysis was fine because, as I said, in the first analysis, the only problem that Salome-Meca had was it was not able to find boundary condition for all the 3, x, y, and z directions. That's why it was throwing an error. Let's have a look at this post-processing file. And here we can see that the maximum displacement that we can find out for the top face for the magnitude is 4.8 micrometers. Let's go in and quickly have a look at dz, which is minus 4.6 micrometers. Now again, let's go in and have a look at the von Mises stresses. Here we can see that the von Mises stresses are a bit high, 1.2 megapascals. But again, as I mentioned earlier, software videos, those 1.2 megapascal or those high stresses are mostly for the corners or the bottom corner of the cube. The center of the bottom face of the cube has nearly gotten 5.2 or 0.52 megapascal or half a megapascal of stress. And as you can see, the top face and everywhere else, generally it is around 1 megapascal. So these are the values for displacement and von Mises stresses for a cube which has the bottom face rigidly fixed in x, y, and z direction and has a pressure of 1 megapascal on the top face. So I hope you liked it. In this video, we just saw how to conduct finite element analysis of a 1 cubic meter cube which is made out of carbon steel or steel and with different boundary conditions for the bottom face. Thank you and see you soon in the next video.